succeeded. Okay, so welcome everyone to this week's Rencontres. So it's a great pleasure to have Shota Komatsu from CERN, who will be giving us a talk on analyticity and unitarity for cosmological correlators.
All right, so can I take off now? Is it okay? Or,
yes. Yes.
Okay, so thanks a lot for the invitation. So yeah, it's nice to be here. The room is rather packed. So today I'm going to talk about my recent work with Lorenzo Di Pietro, who is in Trieste, and Victor Gorbenko, who is right now in Stanford, but moving to EPFL next March, and which is about cosmological correlators, especially the properties of cosmological correlators like analyticity and unitarity. And I should also mention that like around the same time, there are like also papers by EPFL group. So Victor was actually like switched by his future colleagues. And so they are more like interested in like bootstrap aspect, whereas like we explored like a slightly different aspects, but there are like parts which overlap a lot. So let's start.
Maybe you need to click on the yeah.
Okay. I'm not sure which one will work. Okay, now it's working. Okay. All right. So let's start. So this is the plan. So there are basically three topics that I want to describe. The first one is the ADS Lagrangian for it. So like the Lagrangian description, especially ADS Lagrangian description, which automatically generate DS Feynman diagrams. And the second one is based on this observation, like we discussed. I'm going to discuss some analytic properties of correlation functions. And the third one is about the consequence of unitarity, DS unitarity, in the late time correlation function. And the first two is perturbative statements, whereas the last one is non-perturbative statements. Okay, so let's start. So with the introduction and motivation. So I think everyone agrees that ADS-CFT is great. So on the one hand, it gives us like access to the to the strongly coupled quantum field theory from gravity. And on the other hand, like we can learn about quantum gravity for quantum field theory. And more recently, we learned a lot about insights into black holes. For example, like the recent resolution of the information paradox, or like reproducing page curve. Of course, that like a last achievement is not directly like relying on the ADS-CFT, but many insights came from ADS-CFT. So, however, we should remember that we don't live in ADS spacetime, and I actually erased one quote, but there is a quote of like a Juan Maldacena. You can actually watch it on YouTube. Like there was some like a YouTube interview which took place in ICTP, in which he said like we got the sign wrong. Of course, like that what he meant is that like we are actually living in rather DS rather than ADS. So what I meant, yeah, indeed, what I meant by this is that like our universe is more like approximately DS rather than ADS. And there are basically two like periods in which our universe was more approximately DS. And the first one is current accelerating expansion. And the second one is inflation. And this is the one which is more relevant for my talk, because like the features of inflation, especially like the features of quantum mechanics, in this period, you can actually observe from the cosmological observation. Okay, so this is a super oversimplified view of what has been discussed, what is being discussed in DS. Of course, like people know that DS is important. So there have been many works on DS, and there are like well, roughly speaking, there are like two different approaches. And the first one is more like a top-down approach, which is more based on string theory or formal theory. And the idea is to really construct DS metastable vacua in string theory. And the famous attempt is called KKLT. And also like there are many other recent attempts based on orientifolds and some other non-perturbative objects. And on the other hand, there are also more like a bottom-up approach, which is more relevant directly to cosmology and observations. And so here, like people often do choose some Lagrangian and do the perturbation theory, and then like make a prediction of what we measure in the universe. And alternatively, instead of relying on model and doing the perturbation in the coupling constant, people also discuss the effective field theory approach for inflation. And more recently, there have been attempts to kind of systematize this perturbation theory based on more like fundamental principles like unitarity or optical theorem. And that goes under the name of cosmological bootstrap or cosmological optical theorem. And however, like, well, these two approaches both have virtues and also disadvantages. And the disadvantage of the top-down approach is that it often involves some non-perturbative physics in string theory, and it's often hard to justify every detail. And on the other hand, in this like a bottom-up approach, things are often perturbative, either in the coupling constant or the derivative expansion. And also things, well, except for this EFT approach, things are model dependent. So given this situation, I think it's kind of like a good to ask this question. What are general rules of quantum gravity in DS or nearly DS spacetime? However, as soon as you start asking this question, you will realize that we don't actually know the answer to even simpler question, which is what are general rules of quantum field theory in or on a rigid DS background. And this is what I'm going to discuss today. Okay. So to be more precise, let me just list some questions that would be nice to answer from this perspective. So the first question is to understand the consequence of bulk unitarity. So unitary time evolution in DS spacetime, and also the causal time evolution of DS spacetime in the late time correlation functions, which are more directly related to what we measure. And another question is that given some similarity with ADS-CFT correspondence, it's natural to ask whether there is some conformal field theory or maybe conformal field theory without stress energy tensor, because we are not talking about gravitons, that describes the late time correlation functions. And if that exists, then we should also ask what are general properties of such correlation functions, such conformal field theory. So those are things that I want to kind of like try to address. I'm not going to answer all the questions, but I want to address these questions in my talk. And in particular, I'm going to say something about unitarity. But the question about causality, I'm not going to say anything, and I think it's like an interesting open question. Okay, so just to remind us, let me just briefly review the very basics about DS spacetime, just to make sure that everyone is on the same page. So this is the Penrose diagram of DS spacetime. And this is the future infinity, I plus, and this is the past infinity, I minus. And so when describing this,
The Zoom just died. We don't hear anything, and I think Shota's computer died.
Are you in the room, Yusuf?
Miguel, can you hear us? Let me call him on the phone.
Thanks.
I think you're muted. No?
Now we can hear. Now we can hear. Perfect.
Okay, sorry for these technical difficulties.
Okay, so all right, so we talked about global DS. So and then there is yet another coordinate patch people often use, which is the Poincare DS, and which basically covers half of this Penrose diagram. And the metric in that coordinate patch is given by this expression. And as you can see, that this has close connection to Poincare DS based coordinate patch. And the last one is called static patch, which basically covers 1/4 of this Penrose diagram. And I don't write down the metric here, but you can think of it as an analog of Ringler ADS. And as in the Ringler ADS, the physics in the static patch looks thermal. And I'm going to explain why it is so. So, okay, so here, like I explained just the coordinate patch, but because ds is like a time-dependent space-time, we also need to specify which state we are going to consider when we talk about physics. And there is one particular state people like when discussing this ds physics, and that is called like a Bunch-Davis vacuum. So Bunch-Davis vacuum is a state which is invariant under the ds isometry, and which you can define even in interacting quantum field theory. So there is a systematic way to define this Bunch-Davis vacuum even in interacting quantum field theory. And if you consider like a free field theory, then you can actually define more general. It is known that you can actually define more general states, which is invariant under the ds isometry, and those are called alpha states. But at least as far as I know, like there is no systematic way of defining alpha states in non-perturbative interacting quantum field theory in ds spacetime. So the reason why people like Bunch-Davis vacuum is because like it has a nice geometric definition. So the idea is as follows. So you first take this Penrose diagram and cut it into two halves and look at the upper half, which is the expanding part of the universe, and then analytically continue the spacetime to the sphere or hemisphere. And the Bunch-Davis vacuum is defined as a state which you can obtain by doing the path integral on this hemisphere without any insertion. And more concretely, the analytic continuation you need to do is the following. So you take the global ds coordinate patch and then do the analytic continuation so that tau becomes theta. And if you do that, then this theta becomes the coordinate which runs from 0 to pi and which parameterizes the sphere in this way. And importantly, this theta is not a periodic direction because it starts from the south pole and it ends at the north pole. And if you analytically continue this theta to Lorentzian time, then you get the ds space global ds coordinate. And another nice feature of this geometric definition is that it also gives you an idea why the static particle physics is thermal. So instead of taking this theta and analytically continue to Lorentzian time, you can also take like this direction, like this rotation direction phi, which is periodic, and then do the analytic continuation. And if you do that analytic continuation, then you naturally get the time in the static parts coordinate. And so this analytic continuation is very much similar to what you do in the thermal physics. You have a periodic direction, and then you do the analytic continuation. And much like thermal field theory, what you get in the end is the thermal physics. So that's basically like just like a pictorial way of understanding why the static patch physics looks thermal. Okay. So far I described the two coordinate patches, but there is also another patch that I mentioned, which is the Poincare patch. And this Poincare patch is really useful for understanding the relation to ADS spacetime. So this is a Poincare patch, and as you can easily see that if you do the analytic continuation z equals plus minus I eta, you get the metric of ADS times -1. So the claim is that if you do the analytic continuation from ds, then you get minus ADS. And indeed, you get this metric. So, and then we know that like in the case of ADS spacetime, we know that like there is a CFT living at the boundary, which is z equals 0. And under this analytic continuation, z equals 0 is mapped to eta equals 0, where eta is the time in ds spacetime in the Poincare patch. I didn't emphasize this, but eta runs from minus infinity to 0. So eta equals 0 corresponds to late time. So because of this, like it's kind of natural to expect that late time is mapped to boundary of ADS. So there should be some conformal field theory or conformal description that describe the physics at late time. So this is a kind of like a basic intuition why there could be ds, something like ds CFT. But I should emphasize that there is one important difference between ADS and ds. So what is that? So to explain what is the difference, let me just remind you what we do in ADS CFT correspondence. So in the ADS CFT correspondence, we take ADS spacetime, put some field inside, And then you pick some boundary condition of this scalar field, let's say scalar field phi, so that to be given by J, where J is something that you choose by hand. So of course, this is just schematic, and in reality, we need to look off the fall off, like how it falls off in Z, and then pick some appropriate term. But this is some schematic picture. So you pick boundary condition for phi so that it becomes J that you pick by hand. And the claim of ADS-CFT is that if you do the path integral of phi with this boundary condition, and that is going to give you the CFT partition function with source term J. So more explicitly, it's given by this expression, e to d dx, jx or x, where jx is the source term, which you pick by hand, and ox is the operator, which is dual to the scalar field phi. So in other words, ADS problem is a boundary value problem. So on the other hand, what you do in DS is quite different, because what you first need to do is to prepare a state, which is often a Bunch-Davies vacuum state, and you just let it freely evolve in time, and then you compute some observable at eta equals 0. And when you do so, you never fix the field configuration at eta equals 0. You actually need to integrate over all possible field configuration at eta equals 0. So this is what I emphasized here. And in other words, it basically says that DS spacetime or DS physics is more like an initial value problem rather than the boundary value problem. And you can also see this difference, especially the difference in DS from the path integral point of view. So in DS, as I said, what you need to do is to prepare some state and then let it evolve. And in quantum field theory, in terms of path integral, and that's going to be described by what's called Schwinger-Keldysh path integral or in contour. So the idea is to take this kind of time-folded contour, and this part describe Ket, and this part describe Bra. And we insert some observable here. And if you do this path integral, then it automatically computes the expectation value of the observable at late time eta equals 0. And of course, as you can see in this path integral contour, you never fix anything here because it's really in the middle of the path integral contour. And of course, if you really want to fix some boundary condition here, then there is, of course, a way to do that, which is to basically insert the resolution of identity and later sum over all possible field configuration. So this is described in this a second picture. And this picture is essentially just a way of doing the computation using the wave functions, because this part which connects psi to j gives you the wave function psi of j, whereas this part which connects a j to psi gives you the psi star of j. And then you integrate you compute the observable for a fixed configuration j, and then finally integrate out all possible j, which translates to basically a summing over or integrating over the arguments of the wave functions. And if you do so, then you can see now individual wave function looks like ADS-CFT. And because of this similarity, Strominger and in particular Maldacena proposed that the wave function with argument j should be described some CFT, although we don't know what that CFT is, and then it should be given by this expression. Okay. So let me just emphasize, give you some pictorial explanation of what I just said. So what I just said is that in order to describe wave function, you can actually fix the boundary condition because that's the definition of the wave function. And this is more naturally related to DS-CFT. Whereas if you really want to compute the correlation functions, and then you prepare wave function and its conjugate, and then sum over all possible fluctuation at eta equals 0. So if I were to draw a picture, I would draw something like this. Okay. And let me now make some comments and present some puzzles. So this is the wave function description that I gave. So this is what people often discuss in DS-CFT. But I should emphasize that there is right now no example in full quantum gravity, except for some a little bit exotic theories like high spin theory or low dimensional theories like JT gravity. However, I should also emphasize that if you take some quantum field theory rather than quantum gravity in DS, then because if you are putting quantum field theory in DS, you can just do the computation and compute this wave function productively. And if you do so, then indeed, the structure that you get for the wave function is consistent with this kind of like a CFT partition function representation. So this is one nice thing. But on the other hand, this wave function interpretation also gives you some puzzle. So what is that? So let's say we want to compute correlation function using this wave function interpretation, and then try to use the DS-CFT correspondence. According to DS-CFT, individual wave function is given by some deformed CFT partition function. So what you need to do is to take two conformal field theory and deform both of them by finite amount by some source term, and then finally integrate over all possible source terms. And as you can see, this is a very, very complicated manipulation. And it's not even clear that the final answer is going to exhibit some nice conformal symmetry because you are really deforming the CFT by finite amounts by some relevant and irrelevant operators. And so I would say this is not really a CFT computation. However, if you're just talking about quantum field theory in DS, then of course, the DS spacetime has an isometry, which is isomorphic to conformal symmetry. So the final answer should respect the conformal symmetry. The final answer should be kind of representation of the conformal symmetry, which is the DS isometry. So now, yes.
When you integrate over DJ, is there a natural measure?
Yeah, that's another important question, and in general, I don't know. Yeah, of course, like we probably want, of course, we want some. Okay, so in quantum field theory, I think you can work it out, but I don't know like if there is any explicit result which covers every like whole cases. And of course, one thing we want to require is that like this measure should also respect the DS isometry. Otherwise, the final answer is going to break conformal isometry. So the DS isometry. So now the question one could ask is that. Is there any other question? Okay. So now the question one could ask is there a way to see the conformal structure of the correlation functions more directly, rather than going through the wave function and then deforming it, by viewing it as CFT and then deforming it? And there is an answer to that question. And you can actually write down the Euclidean ADS Lagrangian, which directly gives you the correlation functions rather than the wave functions. And that Lagrangian actually contains twice the number of fields as compared to the original DS quantum field theory. And this compactly summarizes findings in the literature, in particular, very nice recent works by Slate and Tarana, who made heroic efforts in understanding the relation between Euclidean ADS Witten diagrams and DS diagrams. Okay, so that's the first topic I'm going to discuss. So the Euclidean ADS Lagrangian for DS. So the derivation is actually conceptually very simple. So the starting point is again this path integral, which directly computes the correlation function, which is in contour. So you take and in this path integral, you naturally have two copies of quantum field theory because you have like two sides of the contours. But I should emphasize that these two copies is not identical to what I'm going to present as a final result. So I said like there are like a twice number of fields, but those twice number of fields is not the same as these two copies. So with that in mind, let me just explain what we need to do in the conventional informalism or Schwinger-Keldysh formalism. So now because we have two copies of fields, so individual Feynman diagrams are now decorated by left or right, depending on you use the vertex from here or from here, from left side of the contour or from the right side of the contour. For example, if you take the phi cube theory and then draw a Feynman diagrams, and then like there are like many possible way to assign like a left or right to individual vertices. So this is one example. And as you can see in this example, the building blocks for doing this Feynman diagram is the propagator, which in this case there are four different propagators: left, 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 right, right, left, or right, right. So what are those propagators? And the difference of those propagators is basically the time ordering. So let's first consider left one. So you basically pick a as usual in quantum field theory, the propagator is basically given by the 2-point function in the free field theory. And let's consider the left one. And if you take the left one, then you can see the order of the path integral is the same as the order of time in this contour. So that's why you naturally get the time order correlation function. So that's why the propagator for left is time order correlation function. On the other hand, if you take right, then the order of path integral is the opposite to the time ordering. So you get anti-time ordered correlation function. Whereas if you get left one, then you can see that in the path integral, right always comes after the left one. So I always put right here and left here. And this object is often called Weidmann propagator because the order of positions of the fields is fixed, irrespective of whether either one or either two is bigger. Okay, so this is just a summary of what I just said. And so let me remind us what realistically we mean by time ordering or anti-time ordering correlators. So as you know, in the usual flat space quantum field theory, the time ordering is correlated with the I-Epsilon prescription. So because basically the order inside these correlation functions, the order of fields inside this correlation function is dictated by the imaginary part of time. And if you want, in the case of time ordering, you want to correlate the imaginary part of these times. Sorry, this should be etas instead of t's with the time eta. And the correct way to correlate them is to just like multiply 1 minus I epsilon to etas. Whereas for the anti-time ordered one, you want to anti-correlate. So you multiply 1 plus I epsilon. And the nice thing about this is that, so if you look, and because of this, then naturally we are led to a conjecture that if you want to have a field from left part of the contour, you multiply eta by 1 minus I epsilon, and for the right, you multiply 1 plus I epsilon. And one nice thing about this is that if you do this rotation a little bit, then left-right also automatically works. So that's something you can just check. And more physical.
So why you say this is a conjecture?
Sorry, it's not a conjecture. It's you can derive it. Yes. So more physically, the importance of this I epsilon is because, like, if you consider Lorentzian correlation functions, they are often like a branch cuts coming from the light cone, and these I epsilons basically tells you how to avoid those branch cuts. For instance, in a particular case of 2-point function, there is a branch cut like this, starting from like x, where x is the magnitude of the spatial position, spatial distance. And what I just said is that for the left correlators, you just need to avoid this singularity, so that by going upwards, whereas for the right one, you need to avoid singularity by going downwards. And as usual, and also in flat space quantum field theory, once we know how to avoid the singularity by I epsilon, then we also know how to rotate to the Euclidean spacetime. So that's what we also do when you do the computation of the Feynman diagrams, right? We rotate everything to the Euclidean momentum so that you don't hit the singularity. So here it's the same. So if you now want to analytically continue or relate to the ADS spacetime, then you need to rotate those points in such a way that it avoids this singularity. So which means that for the left one, I need to rotate it in this way. For the right one, I need to rotate it in this way, downwards. So, and then once we understood how to rotate things, then we just take the expression of left, right, and left-right correlation functions people studied, because these are just like propagators in DS spacetime, so people actually compute it. And everything is given by 2f1, hypergeometric function. And if you do the analytic continuation, then you discover that after the analytic continuation, each object is given by a product of two ADS propagators, and one corresponding to dimension delta, and this delta is correlated with mass of the DS field, and the other corresponding to d minus delta, which is often called a shadow of the original dimension. So the summary is that up to a phase, basically all these three propagators in DS is given by a linear combination of two different fields in ADS spacetime. So this relation itself was derived already in Slate and Tarana using the Millian-Barnes representation. And here I just redid their analysis based on a more direct coordinate space approach. So this basically gives you one relation between DS and ADS, but I want to do a bit more. I just want to rewrite everything into ADS Lagrangian. So how do we do that? So we have this relation. So now step one, I split phi left and phi right into two. So now I have, instead of two fields, we have four fields: phi left delta, phi left d minus delta, phi right delta, and phi right d minus delta. And then I impose that phi left delta, the 2-point function of these two operators in ADS spacetime or Euclidean ADS spacetime reproduces this one. And I also impose that the left to right delta delta reproduces this one. And for example, if I want to analyze, and then if I change this delta to d minus delta and this delta to d minus delta, I impose that it reproduces this g d minus delta ADS e I pi d minus delta. So, and then let me just remind you that by splitting, I really just mean this one. Phi left equals phi left delta plus phi left d minus delta. And because of this, the interaction vertex, which was originally just given in terms of left field, is now written in terms of the linear combination phi left delta plus phi left d minus delta. So now I have a matrix of propagators, so I can just invert it and read off the kinetic term. And if you do that, then write down the Lagrangian using this interaction vertex, then you discover that the 2 out of 4 fields decouple. And this 2 is some linear combination of phi left to right delta and phi left to right d minus delta. And then once you realize that 2 out of 4 fields decouple, you just write down the Lagrangian in terms of the remaining fields. And that leads to this representation. So this is some linear combination of a left delta plus right delta. And this is a linear combination of left d minus delta and right d minus delta. And so, yeah, so this is what I wrote here. And now, because we wrote everything in terms of some weird linear combination. So now the interaction vertex gets a bit more complicated. So it's given by some weird linear combination. Okay, but this is the answer. And the good thing about this answer is that you can now take this ADS Lagrangian and just forget about everything about in contour or Schwinger-Kirdish or DS spacetime, and just do the computation in the usual way, like you do in ADS splitting. Yes.
Can you go directly from phi left right to phi plus minus?
In some sense, yes, because what I did is to split into 4 and then recombine it to phi plus phi minus, and then 2 things that decouple. But two things that decouple in the end probably won't contribute to the computation because it decouples. So I think you can write phi plus and phi minus in terms of phi left and phi right. Yeah, we didn't do that, but I think it's possible.
They have different masses. No?
They have the same mass, but the boundary conditions are different because delta and d minus delta are related by the change of the boundary condition. Yeah, thanks for asking. That's an important point.
So do you have some gauge symmetry now?
We don't have gauge symmetry. And I think a gauge symmetry is related to the one we threw away.
So you have twice as many fields.
Yeah, we had twice as many fields, and then I eliminated the unnecessary 2, which would correspond to gauge symmetry, you would say. So now what is left is some weird linear combination. of the original field. Okay, so this reproduces and extends results obtained by a very nice set of works by Slade and Tarana. Okay, so let me just make one comment, or maybe two comments. And as you can see, this is very sick as an ADS Lagrangian. Well, first of all, there is minus sign. So in no situation, both terms come as a positive sign, which means that like one of them is what people often call ghost, like negative kinetic term. So of course, like this poses a problem probably for non-productive physics, but productively it's okay. And I wouldn't exclude the possibility of using this for non-productive physics, but in that case, you really need to carefully discuss what is the contour of integration for these fields. And this is what I said, like as a theory in ADS, it is certainly non-unitary. Because
I mean, the Schwinger-Keldysh Lagrangian has this form, but this is not the same.
Right, so that's a tricky point. It's not the same. So also in the Schwinger-Keldysh, we have left right, and you combine it like a left plus right and left minus right using the what's called Schwinger-Keldysh rotation. It's not the same rotation because now it involves extra step, which is to analytically continue to ADS and then see what remains. And this introduces various factors like this one, which you never see in the usual Schwinger-Keldysh. Okay. Sorry, was this? Yeah, okay, so, right, so let me just make a comment. Okay. So the second comment is more speculative. And so for the wave function, so I was emphasizing that for the wave function computation, we fix the boundary condition at future. And whereas for the correlation function, you never fix the boundary condition. And they use integrate it out. And now it's a kind of interesting to ask what is the flat space analog of what we achieved? Because what we achieved is that although original object is not something like ADS, because you integrate over it like fields at the eta equals 0, but at the end of the computation, I converted this computation into something that looks like ADS, which is more like this. So that is a bit interesting. And given that, it's kind of interesting to ask whether something like that is possible also in flat space. So what is the flat space analog of psi j? So in the flat space analog of psi j, I would say that it's more like S matrix because I fix the initial state and out state, in state and out state, and a computer matrix element. You never sum over like an out state and in state if you're just interested in S matrix. On the other hand, the analog of this correlation function is more like an inclusive observable in which you sum over states, out states, like a differential cross-section or energy-energy correlator or event shapes. So given this similarity, then it might be interesting to ask if there is a more direct way to compute these inclusive observables in such a way that it looks like S-matrix computation. Because so far, when people compute inclusive observables, even when comparing with collider physics, what people do is to first compute S matrix and then square it and then do the phase-space integral. And it's probably interesting. But if there is an alternative way to directly get to the inclusive observable, that might be interesting. And in here, like I just wanted to mention that there is actually recently like an interesting attempt in this. So this is actually a PH paper, in which they kind of combine various techniques to directly try to get the representation of the inclusive observables. But this is more like a combination of technical tricks, and it would be nice to understand what's happening behind it physically. Okay. So any questions so far? All right, so let me now move on to the second topic, the analyticity. So here I try to be a bit brief. So now I derive some relation to ADS Lagrangian. So given that relation to ADS Lagrangian, it's kind of like natural to speculate or conjecture that the late-time 4-point function has at least some similar structure as the boundary 4-point function in ADS, which was not obvious before rewriting things into ADS. Of course, like this relation I only established perturbatively, so this should hold only at the level of the perturbation theory. In particular, we want to claim that it is natural to expect the conformal block expansion exists for the late-time 4-point function. So let me just try to be precise what I mean by this. So let's take like a late-time 4-point function. You put 4 operators at late time eta equals 0. And as I will explain in the next topic, just using DS representation theory, it is natural to expect that that object has this representation, which is integral along what's called principal series representation. There can be some corrections, but here let me just, for simplicity, focus on the principal series. And so where this C delta is contains dynamical information, and F delta is something that's determined by the symmetry, which is basically conformal partial wave. But if you just use the DS representation theory, it doesn't tell you what is the function of C delta away from the principal series axis. However, given this connection to ADS, it is natural to assume that this C delta should behave in the same way as the C delta for ADS boundary correlation functions. And for the ADS boundary correlation function, we know that the C delta only has poles. And because C delta only has poles, you can often like deform the contour and rewrite everything as a contribution from poles. And that naturally leads you to the what's called conformal block expansion, which is the most natural representation for the ADS 4-point function. And I should emphasize that this discrete representation is not guaranteed from the DS point of view. But if you use the relation with the DS, then it suggests that this kind of object representation should exist. Okay. And however, I should also emphasize that even though I kind of like argue that there should exist such a discrete sum representation.
Sorry.
Yes.
Is this consistent with the Sitter isometry representation theorem?
It is consistent. I'm going to explain that point in the next topic, but the basically DS isometry representation tells you that this C delta evaluated on the principal series must be positive. Whereas here I'm talking about behavior of C delta away from the principal series. And it can have poles away from principal series. Okay, so I should emphasize that this object doesn't actually have a natural physical integration. It's actually related to your question indeed. So in ADS, we know that this object has a very, very clear physical interpretation. Basically, that corresponds to sum over states. If you can show it by using the state operator correspondence, because you are just like inserting some resolution of identity and then using the representation theory of ADS rather than DS. However, in DS spacetime, such an interpretation doesn't exist because, because the constant time slice in DS spacetime is naturally related to DS isometry, representational theory of DS isometry, which does not include these delta primes, like a discrete delta primes. However, we just wanted to suggest that there might be some possible interpretation, at least physical interpretation, and some quasi-normal modes in static patch. So this you can see it by looking at some simple Feynman diagram, let's say like an exchange diagram. And so this representation, the good thing about this representation is that this kind of like a conformal block-like representation gives you kind of information about large distance expansion, much like what happens for the usual conformal block expansion for conformal field theory. And if you consider this kind of simple Feynman diagram, which is the exchange diagram, then you can see that the large distance behavior is indeed actually dictated by the large distance behavior of the bulk 2-point function. Of course, this is very special to this particular diagram, but this is true for this particular diagram. And now, another observation is that the large distance behavior of this 2-point function, large space-like distance behavior of this 2-point function is also related to the large time-like separation of this 2-point function inside a static patch. And if you write this large time-like separated 2-point function in the static patch coordinate, then you get this kind of expression, e to minus t times delta, and these deltas are same. And this has a natural interpretation as a summation over the quasi-normal modes in ds spacetime in the static patch. So at least in this case, like there is a natural connection between the conformal-like expansion and the quasi-normal mode expansion. Of course, this is just observation, but I think it would be nice to kind of try to explore a bit more. Okay, so any questions before moving on to the last topic? So now the last topic is about unitarity. So now I'm not going to talk about the perturbation theory. I'm just going to talk about more general properties of the implication, the implication of the bulk unitarity in late time correlation functions. So to understand it, let's consider the simplest object, which is the unitarity of the 2-point function in flat space. So you take 2 fields, and then compute the correlation function, 2-point function. And the first step is to write this in this way. So where p hat is just the translation operator. And the next step, we use the fact that vacuum is invariant under the translation. And if you use that, then you can rewrite everything into this expression. And then the third step, we insert the complete basis written in terms of momentum eigenstate. And then now we can replace this p hat with the classical number, C number, P. And that leads you to this expression. And as you can see, apart from this factor, everything what's left is a square of some matrix element, absolute value square of the matrix element. And if the theory is unitary, this object must be positive. So this basically tells you that unitarity in this simplest setup translates to the positivity of the Fourier coefficient. So let's do the same for ds. Now in the bulk 2-point function. So for simplicity, I'm going to take 2 fields at the same time slice, but this is just for simplicity of the explanation. You can generalize to more general configuration as long as 2 points of space-like separated. Okay, so now I'm going to proceed in a similar way. So now I will write this phi x theta, which is at arbitrary points, in this way, where gx is some isometry of the ds written in an operator form. And we pick some reference point, x0. And now, as a second step, I use the fact that Bunch-Davies vacuum is invariant under the isometry. That was the definition of the Bunch-Davies vacuum. And if you use that, we arrive at this expression. And now we insert a complete basis of states written in terms of like an irreducible representation of the ds isometry, which in particular includes what's called the principal series representation. There can also be some other representation, but let's just focus on the principal series representation for the simplicity. So now I get this expression. Well, to be precise, I'm actually making some assumption here. So I'm kind of choosing some basis which diagonalizes this particular combination, but that you can always do. And I should also emphasize that this representation nu and this representation nu, in principle, like it looks like I'm inserting 2 resolution of identity, but these representations must be the same because it's a definition of the irreducible representation. If this isometry takes you out of one particular representation, that means that it's not a representation. So this is a little bit schematic, and one can we did in the paper a bit more precise way. But the important point is that this part is completely determined by the symmetry because you are just evaluating some group element and sandwiched by the irreducible representation. And you can even write down some differential equation for this object and solve it. And if you solve it, then you discover that it's given by some ds harmonic function or ds propagator. Yeah, well, depending on, well, normally it's called ds propagator, but basically it's like harmonic function. Well, okay, so this comment is a bit confusing probably, but okay, it's a ds propagator. So it satisfies the Casimir equation. But anyway, so, and the important point is that the coefficient, now, again, you can rewrite it into something positive, like a square of absolute value square. So this also tells you that, so if you decompose this 2-point function in terms of this object, which is completely determined by the symmetry, the coefficient must be positive. Yes?
Excuse me. The extra terms that you must add to get integrated,
Yeah, there are.
it depend on the theory or it's just group?
It's a group theory, and it's classified, but typically like there is a huge possible representation. For example, in addition to the principal series, there is also one called complementary series, for which the dimension is real, 0 to d minus d over 2, I think. And there, if you go to higher spin, then there can be some other representation, like a discrete series.
In principle, you should include them all.
Yes, we should include them all.
So what is this psi and why doesn't GNU want?
Oh, psi means that it can be that if you take one theory, that theory can have several different states with the same representation. So psi is a kind of extra label.
And this because you have a move psi there with the definition of GNU, this you move the sum over psi.
Right. So okay. So
this GNU.
Yeah, indeed. So this part, although it, for individual psi, for each psi, it's okay. So this part is completely determined by nu because it's a symmetry of determined by the symmetry. So this part doesn't depend on psi. But psi comes here. I forgot. Okay, so
but then so in general you have to sum over all these empty ranks, not just the principal series, and
right.
Each of them will have positive coefficient.
Yes, each of them have positive coefficient. But the good point is that I can also individually look at each representation. Another comment I wanted to make is that this proof only relies on this property. So if there is any other vacuum which is invariant under ds, that also satisfies this property. So pictorially, what I did was the following. So, well, I like draw this picture, but I'm not sure if it's useful. But so originally I was putting 2 points in at the same constant time slice. But for the purpose of drawing picture, it's kind of useful to put one of them on this side of contour and the other to the other side of contour. So this is the same as putting 2 points here because this part of the path integral just cancels out. And now from the picture I was advocating, it's a bit like considering this picture because we are constructing bra and ket and put operator x1 and x2. And then what I did is to do some isometry and move things to a canonical point. And now this part looks like positive because it's something square, and the rest is some kinematical factor which comes from this motion, like movement from x1 to x0. And now I can do the same for the 4-point function. And for the 4-point function, now we are considering late time 4-point function rather than bulk 2-point function. So initially I want to put all 4 points at theta equals 0, which is here. But for the purpose of drawing the figure, I prefer to put 2 of them below and 2 of them above. And then insert a complete basis of states here. And in equation, what that means is that I take this 4-point function and then insert the resolution of identity here in the middle. And now
So I'm confused. Why can you just move these points to one side? Doesn't this correspond to having this phi left or this phi right? Or can you just move them from one side to the contour to the other.
Why can I do that?
Yes.
So
Are these different observables?
okay, so here, like I'm really inserting two objects at equal time slice, and I'm assuming that they are space-like separated. So they actually commute, and in fact, in terms of path integral, this part of the path integral just cancels.
But isn't this supposed to be this phi L, phi right 2-point function?
That's true. That's true.
But now when you move it to the left, then it would be phi left, and that's supposed to be different from phi left, phi right. So,
but the important thing is that those differences were time ordering, and here I'm putting a 2 points. Space-like separate.
Everything is space-like, okay.
And that's also true for this late time because everything is on the late time slice and every points are space-like separated. Okay, so now the next step is rewrite this phi x1, phi x2 as phi 0, phi 1. These are two canonical positions acted by this G12, which is some particular group element, which moves 0, 1 to x1 and x2. This you can always find. And then you do the same for x3 and x4. And then I again use the fact that the omega, the Blanch-Davis vacuum, is invariant under the isometry, and then go through the argument that I presented for the 2-point function, and I get this expression. So now the final answer consists of two parts. The first part is the square of something, which must be positive. And I have this factor, which is completely determined by the symmetry. And this object, again, I can even write down some like a differential equations or conformal Casimir equation. And as you would expect, and this object, which is determined by the symmetry, coincides with the conformal partial wave. And let me just remind you one important property of the conformal partial wave for those who knows the stuff. Okay. And so for the conformal partial wave, so is the solution to the Casimir equation, but typically you need additional input because the Casimir equation is a differential equation. We need to fix some like additional input. And what selects what people call conformal partial wave is the single valuedness under the like movement of position x1, x2, x3, x4 in the Euclidean plane. And this is what we need here because we are just inserting 4 operators at late time slice, and there is no time here, and it must be single valued. So that's why like we naturally need to impose this single valuedness, and that leads to the conformal partial wave. So this is a summary of what I said. So it also answers Anne's question. And so this is the summary of the structure of the late time 4-point function. So it's going to be given by integral over the principal series plus some extra stuff, which Benjamin was mentioning. And the important point is that from the unitarity, we know that C nu evaluated on the principal series must be positive. So this is a non-perturbative statement. And from the perturbative relation to ADS, we can argue that C nu evaluated away from the principal series axis must be meromorphic.
So basically the difference from the usual CFTs is just in the positivity properties of this function. Because usually you ask for the residues of the points to be positive, and here it's...
Exactly. So yes, in the usual case, we know C nu is, in the usual CFT, we know C nu is meromorphic, and in addition, we require that residues are positive, but that we don't require here. But so let's say, so there is also, let's make one comment, which is, and there is also a possibility of generalizing what I just said. So here I was like putting 2 operators below and 2 operators above, and then using the fact that this looks like a positive object. But in principle, we can also consider a kind of matrix of like overlap, like 1 operator here, 1 operator here, 1 operator here, 2 operator here, like this. And this matrix should also satisfy some kind of positivity constraint because this is a matrix of overlap in the unitary theory. we can also increase the number of points to like 3 points up and 2 points down. That is going to give you some positivity relation, including the 5-point functions. So this is something one could explore, but we didn't explore. And
But here, do you have in mind having the points on the boundary or in the block? Because
so here I had in mind points on the boundary, but I just like a default moving away from the surface by epsilon, which doesn't really matter.
But then should this buy you anything from the CFT? I don't think it does. In the usual CFT, this would not give you anything.
In the usual CFT, yeah, right.
Because the competition previously that you did with the 2-point function, it was interesting because it was in the bulk. So this is positively like at the boundary operator expansion.
Yeah.
Now you're getting positivity OP. So 2, 3, and 4 points. I don't think it.
Yeah. Okay. So 2, 3, 4 probably doesn't buy you, but like that. So this at least gives you like a generalization to 5 points.
Sure.
Okay. So this was some speculative comments about observation, which I skip. So let me just conclude because I'm over time, even including probably some time we spent for the technical difficulties. So the conclusion is that we basically proposed a systematic approach to relate DS and ADS perturbation theory. And from that, we understood some part of analyticity, which is based on the perturbative argument. And we also presented some unitarity constraints, which is non-perturbative. And because we now understood positivity constraints in unitarity constraints, it's also natural to try to set up bootstrap. And that's what like an EPFO group explored a little bit in a simple toy example. But there's much more to be explored. But for us, what's more interesting is to include gravity. And I should emphasize that including gravity now changes the story drastically. In ADS, including gravity was not that different from the point of view of conformal bootstrap, because having gravity or not just translates to the fact whether we have the stress energy tensor in the bulk or on the boundary or not. It's just like a one change of the operator spectrum. However, in DS, it's quite different. And this difference you can also, you can summarize in this perturbative diagram. So this is the graviton exchange diagram between some, let's say, scalar. And if you look at this, so there are like a several diagrams again that you can draw, because again, we can put this vertex here or here. So if you put both vertices on the same side, then it does look like a bit like ADS diagram, and it doesn't poses any conceptual problem. But if you put one vertex here and the other vertex here on the opposite side, then you can see that this graviton actually passes through this late time surface. And this is like a gravity wave passing through this like a late time surface on which we are measuring the distance. So this basically means that like this diagram could change the definition of the distance. So we also need to refine the definition of the observable perturbatively. So even defining what is perturbatively well-defined observable is a little bit non-trivial. Of course, I believe one can deal with it, but we need to think about this. So this is the comment that I wanted to make. And another one is the flat space analog, which I already mentioned. So the question is like whether there is some nice way to understand inclusive observable. So with that, let me end my talk.
And we have time for questions.
This problem arises if the surface is tiny, fixed, not infinite.
Yeah, you mean like yeah, this problem also arises yeah.
Also has the infinite time.
You mean, well, so this problem, I think it arises even for infinite time, because graviton fluctuation is still there at eta equals 0. So that's one difference from ADS, where things got frozen at the boundary.
So I didn't follow the logic from one part. conclusion of part 3, I think, was that there is Lagrangian, which is similarly non-unitary.
Mhm.
And then you will go to unitarity, and what's the connection?
Oh, it's not, there is no direct connection. It's a separate like results. They are separate results. So like typically when formulating S matrix or conformal bootstrap, like understanding analyticity, both analyticity and unitarity are important. So here we could say something about unitarity from non-perturbative argument. On the analyticity side, we didn't have much, but we had some argument based on the perturbative relation to ADS.
I want to describe physics in DS, regardless if it's easy or not. Do I need to impose DS isometry? Why is that a natural isometry to it? I mean, it's natural, of course, but why would I want to do it physically?
Yeah, I agree. Yes. I totally share that feeling, and that's why I want to first understand gravity, including gravity, because that also typically involves the breaking of DS isometry. So to be real, okay, to be really honest, well, this is recorded, but like I have a mixed feeling about pushing this bootstrap approach to QF in DS.
So I have a question. So in the end, you wrote this Lagrangian in terms of these mixed fields, but the observables that you want to compute in the end they are correlators of this phi L and phi R, right?
Right.
So why couldn't you just have worked with a Lagrangian? It could also be a Euclidean Lagrangian. Euclidean ADS Lagrangian for phi L and phi R. It would look basically like what you wrote, but with some different boundary conditions in all of the fields. So why does it buy you to write it in this way?
Oh,
in the end, you still have to take some linear combinations of these fields.
Yeah.
No?
Sorry. Yeah, let me think. Okay, so
Is it just that technically we are used to doing these ADS computations where fields have propagate, where
Right.
the propagator has a definite scaling dimension instead of linear combination?
but I think like it's kind of okay also to try to think about inserting some operator which gives you some definite scaling. But even if you do that, like okay, so you're saying that okay, we all
effectively when you look at propagators in the bulk, you still have both fields propagating.
Right.
So your effective propagator will still be linear combination.
right.
So
Yes.
it seems like the computation will be equally complicated.
You mean like okay, you are saying that but technically we're like evaluating the loop diagrams or like more complicated diagrams, evaluating things directly in DS is complicated, and typically we just like in the end we often rotate to ADS. So I would say we end up with the same kind of like
yeah, but I guess my statement is that once you know what is the correct way to analytically continue, yes.
Oh, okay, yeah, that's absolutely true. Yeah, of course, we can individually draw a diagram and then like individually rotate in a correct way, and that gives you the answer. Yes. So this is like the ADS Lagrangian is just kind of like a way to forget about everything. Just like a systematically say like implement in a computer code or something.
Because these people, Tarona and Slate, had they figured out that the decider propagator?
Yes. Yeah. So one conclusion we wanted to draw from this is that this analyticity, which is more like directly related to ADS structure, rather than like individually mapping to fields.
Even that, is that obvious? Because now the scaling dimensions are all complex.
Well, so the poles should show up in the complex places, but the question is whether we have counts or things.
Okay. If there are no more questions, let's thank Shota for a very nice talk.